Hello everyone, and thank you for joining us for the webinar today. My name is Ben Hutchins and I am part of the marketing team here at Innovise. Today we are focusing on the topic of improved planning for sustainable drainage with faster results. If you have any questions as we run through the slides today, please type them in the question box located in the right corner of your GoToWebinar interface. We won't mention your full name when reading your questions, and our experts will provide answers. Please note that all phone lines are muted during the webinar today. Now let me introduce you to your experts. Firstly, we are delighted to be joined by Sama Mohindes, Principal Project Manager at Innovise. Sama is a chartered civil engineer and accredited project manager with over 9 years experience of drainage and SuDS design in both project management and technical management roles. Sama has undertaken, led and managed extensive feasibility studies of highway, railway and airport infrastructure implementation, including the detailed design, cost estimation, cost-benefit analysis and hydraulic modelling for SuDS and traditional drainage systems. Sama has taken team management, project management and bid management roles, leading successful multidisciplinary bids and managing cost, programme and quality of major infrastructure projects. He is also working towards a PhD in sustainable drainage systems at Imperial College London, where he is applying his industry experience in academia to bridge the gap between research and industry. Joining Sama as your host today is Peter Coombs. Peter is Innovation Manager at Innovise. He is a Chartered Water and Environment Manager with 44 years experience. Peter has designed, modelled and delivered a range of storm and foul water networks in the UK, before moving to the Middle East for 5 years. For the past 18 years, Peter has been with the Innovise Group, specialising in SuDS, floods, asset management and AI across the EMEA region. That completes our expert lineup for today, so let's start the show. Peter, over to you.
Lovely. Thank you, Ben. Welcome, Sama, and welcome one and all. Thank you very much for joining us. The webinar today will last about an hour, and we'll move on to the first slide because what we'd like to do is to encourage some audience participation. So if you can move on to the next slide, Sama, you'll see that there's a little question box that would have popped up when you logged in. So if you'd like to post any questions in there, after my very brief introduction to Sama, I will then take a look at all the questions and then field them at the end. So hopefully we'll have plenty of time to answer those burning questions that are coming through. And if you have any kind of comments as well on how things are going, then I'd be really interested to hear how you're finding the implementation of sustainable drainage systems, which has been a passion of mine for my whole working life. I need to update my bio for you, Ben, because I've been with the company for 20 years and it's been 46 years in the industry now. So yeah, interesting. Thanks, Sama. We'll move on to the next slide and find out who is actually on the call today with us, so we can run the first poll and see what kind of background you are from, nature of your organization. So are you hooked in from a local authority, from a water company, consultancy, developer or other? Just come back from 2 days at World Water Tech, meeting a lot of water companies and consultants in particular over the last couple of days in London, with some really interesting presentations on where the water sector is going in the future. Climate change and sustainability and improvements to the environment being high on the agenda. Lovely. Hey, what sort of percentage have we got voting there, Ben?
We're at 80%, Pete.
There we go. Let's close the poll and see what we got. So 69% consultants, so heads down, reaming out these projects left, right and centre. 16% local authorities, being the approving body, and water companies. So we've got a nice mixture here, and some developers too, but all welcome. Thank you very much. If we want to move on to the next slide, Sama. So really, I mean, before I hand over to Sama, the key thing that I would say is that in my experience over the last 40 odd years, one of the major things that we've kind of failed to do to mitigate against future to provide resilience with sustainable drainage systems to mitigate against future climate change impacts, etc., is a failure to spatially plan out those systems that will manage the surface water when things go wrong. We've been very much in the mindset of pipe systems, pipe down to a pond kind of control, and in the future, that's just not going to cut it for resilient communities. So the spatial planning, making the space for the water, all these kind of things have been something that we've been trying to encourage people to do for many years. And I feel as though now, correct me if I'm wrong, but I feel as though the legislation, the guidance is all kind of backing that up. And you're maybe being forced to look at things in a slightly different way, depending on where you are in the country and the nature of your development. So without further ado, I am delighted to be able to hand over to Samra and look forward to your presentation and demonstration, Samra, on your experience. Thank you very much.
Thank you, Peter. Good morning, afternoon, and good evening, everyone, whenever you're watching this. And welcome to this webinar on how we can improve the way we plan and design SuDS faster, more agile, and with confidence. Now, I'd like to start this with talking about how with population continues to outpace the capacity of water systems, and we keep getting the urban creep that continues to wipe the green space, as well as the climate change that keeps hitting us from all different directions, sea level rise, more rainfall, higher intensity. We need to change the way we think about flooding or flood mitigation. And obviously, we have seen, from what we have seen so far, that the gully pipe solution is not working, as Pete has just said. It's not going to cut it, and it's not working anymore. And treating the rainfall as a waste product, shooting it downstream as fast as possible is not a good idea, and it's not working. Because when the water level within rivers are getting higher really quickly, we end up with flooding in the upstream system. Talking about climate change, let's not forget that in the UK, in February 2020, we've had 400% the average 30-year rainfall. And in May 2021, we've had 200% the average 30-year rainfall. Where in Germany, they've had 600% the average 30-year rainfall in July 2021. I mean, and we heard about death situations, and was a very unfortunate event. Now, this makes us rethink about the way we need to handle the situation and how we're gonna look at flood mitigation projects as we move forward. Because maybe if we update our statistical analysis, the 30-year storm is not a 30-year storm anymore. Maybe it's if it's happening quite frequently, and if we now look at our statistical analysis, maybe it's a 5-year storm now. So it's really, really important to change the way we think about this. And in the last 10 years or so, we've come to realize that we need to slow down the urban catchment response. We need to hold on to the water during the peak of the storm, and this will be achieved by what we call in the UK SuDS, or Sustainable Drainage Systems. So I'd like to kick this off with a poll to see what people think about the impeding factors that stand in the way of SuDS implementation. So my question is, if I go to the next poll, in your opinion, what is the most impeding factor for SuDS implementation? Do you think it's resistant clients, or is it a constraint site, or maybe higher construction cost, or maintenance concerns, or maybe lack of certainty and confidence in SuDS? So once we see the results, I will share with you the most common reasons that I've heard over the last 10 years on why people are not pushing for SuDS.
And the other thing, Sam, I would say, if there's anything else that we haven't sort of covered in the questions, if there's another reason for why, feel free to pop that in the question box, and we can share that out with everyone at the end.
Definitely, yeah.
A nice high proportion. I think we're stuck on the 80% of the audience is big audience. Thank you. Thanks, Sam.
Oh, thanks.
So there we are. I think that's an interesting mix there, Samra. What do we
Yeah,
make of that? Is this been your experience, your personal experience as well?
Yes, a lot of people blame constraint side, and from what I could see, that this is, I think, highest or the most common reason why people are not pushing to SuDS. Now, I myself used to blame clients. I used to say, "Oh, my clients are concerned; they don't want SuDS," and we jump when they say. But I've recently realized that it is my duty as a designer, or when I was a designer, to inform clients and give them the reassurance and help them make an informed decision. So in this presentation, I will share the common 6 reasons I've heard from designers and clients why they don't want SuDS, and we will maybe have a discussion and iron out some of these reasons, or hopefully all of them.
Yeah, it's interesting because that is very, very, I mean, plus or minus, you know, between the 5 different options there, it's either ranging from 17% to 26%, so very slightly in favor, if you like, of the site constraints. So it's just literally where we can't physically get our heads around how we can implement sustainable drainage systems. That's the major issue. I think if we'd have run this poll a few years ago, we would have had a completely different set of answers. I think there would have been like clearer, you know, resistant clients would have been probably top of the poll, as you mentioned. But that's really interesting. Great. Okay, I'll say no more and hand over back to you, Simon.
Thanks a lot, Pete. So reason 1, people used to say, my site is steep, I cannot get SuDS in. If I have SuDS here, the volume within SuDS will not be utilized. Well, stay tuned in this presentation, because we will cover this aspect during the demo, and we will model a solution that ensures a proper utilization of storage in steep sites. And this could be a check dam, as you see on the screen here. So when we implement the check dam, we have some sort of an orifice, and we have the top of the check dam will act as a weir, and this is one way of ensuring the utilization of the swale. I mean, if we're looking at storage, or let's say rain gardens, etc., we can do some sort of compartmentalization, and we can divide the rain garden into compartments at different levels. And we've done this in the past, and it worked perfectly fine. So steep site is not a concern, and there is a whole section in SuDS SuDS manual about how to deal with steep site, how to deal with sites with challenging conditions, basically. Another reason I heard that, oh, my site is congested with utilities. Well, the first answer to this is spatial awareness equals adequate clearance. Now, when you are aware of your SuDS footprint as you're making decisions, and as you're scaling up and down and iterating the design, you can see where your SuDS is, you can see where the utilities are, and then you have then the knowledge, or you communicate with utility undertakers. You talk to British Gas, ask them about what clearance they want from their gas main. You talk to BT and ask them what sort of clearance. Can you expose their utility or not? Can you do something? Can you do this? Can you do that? And once you have this discussion, it will inform your decision. You will be able to fit your SuDS. And don't forget that you can incorporate a lot of utilities within your SuDS layers. So, but of course, I'd stay away from high pressurized gas mains and high voltage electric cables. But a lot of utility lines can be incorporated within the soil layer of SuDS, or within any SuDS layer. Another reason people talk about is, oh, I cannot infiltrate, so I'm not gonna implement SuDS. Well, yes, high groundwater table, impermeable soil, proximity to building foundation, or being on the top of source protection zone can impede infiltration, of course. Now, we shouldn't infiltrate if we're on top of SBZ, especially if we're picking a highway runoff. And sometimes we're worried about some sort of structural problems with the foundation, especially if we are sitting on top of choke. Maybe there is some sort of dissolution features that we don't want to develop. But the answer for this is SuDS doesn't have to be infiltration SuDS. There are other types of SuDS. We're going to talk about them today that you can consider. They could be storage SuDS. They could be conveyance SuDS. So you can block the infiltration. You can line your SuDS. You can line it from one side if you're worried about a certain side that is close to the foundation or to highway structure, and allow infiltration from the other side. I mean, that would hopefully iron out the problem. Another reason people talk about is the location. So if you're near an airport, you cannot have SuDS that attract birds and some sort of wildlife. And in this instance, yes, we shouldn't have a pond, we shouldn't have detention basin and a swale, etc. But we can still have an infiltration trench. We can still have a rain garden. So consider other types of SuDS that doesn't attract birds and whatnot. Now, other reason I heard as well is the cost and maintenance. They say, oh, the client is worried about the cost. They don't want high maintenance features. And my response to this is, have you calculated the cost of flooding? And a well-designed and a well-constructed SuDS is not extremely more expensive than an equivalent landscape feature. I mean, when we talk about a couple of inlets and a couple of perforated pipes, that it will not blow the budget, but a destructive flooding will definitely blow your budget. And the final reason is the lack of confidence in SuDS. Now, this basically it especially manifests when we look at the site level or a catchment level. We still don't know, for example, the basic parameters. Let's say length. I don't know if you can see my cursor on the screen, but if we look at the length of this swale that connects these 2 points, is it the meandering length? Well, if it is, when the swale is full of water or surcharge, maybe the water will take a different route. So the length, the slope, the flow route, the roughness could be different. It depends depending on the vegetation, the permeability, the hydraulic behavior. So a lot of basic parameters we're not sure of when we look at the SuDS at the site scale or at the catchment scale. So my response to this is, don't worry too much about this. As long as you understand the function of SuDS, what you're trying to achieve, when I say function, means if you're trying to have some storage, then okay, think about the volume, think about the storage and the levels, etc. If you're trying to convey the water from A to B, then okay, you need to think about the length and the slope. Maybe you can do some stress testing for various scenarios. If you're trying to infiltrate, then okay, look at the soil, look at the layers underneath, and what can happen. Introduce maybe a clogging factor and all this, and rely on the SuDS guidance available. In the UK, we have the SuDS SuDS manual, and I call it the SuDS Bible, and it's an amazing guidance. I mean, whatever you need when it comes to SuDS, you can open the manual and you can find something related to this. You can find an equation that you can investigate and use a hydraulic modeling software to gain more confidence, especially when you're trying to connect various SuDS features together and plan SuDS at a master plan level. And ask questions and discuss with experts. You're going to be surprised that a lot of experts on LinkedIn or your colleagues in your organization or everywhere will be extremely happy to help. And I saw on LinkedIn a lot of people passionate about SuDS, and if I ask a question, I get 10 responses in one day, and not from only my colleagues, even from people in other organizations. I can see a lot of passionate people about SuDS, and you're going to get a lot of help. So don't worry if you don't have this 100% confidence. Don't worry. Understand the functionality. Rely on guidance. Rely on experts and use a software that allows you to visualize and have more confidence in what you're doing. Now, remember that you can always have safety features in your SuDS. So, for example, whenever I design any rain garden or a SuDS feature, I normally have this spigot and a vertical pipe that can allow water to bypass the soil, so the soil doesn't become a bottleneck for the water, and take the water directly either to the storage layer or maybe a gully. So your SuDS can become a gully when it's overwhelmed. So basically, if you flood, you're going to have to think about other elements in the system to blame than SuDS. And yeah, as I said earlier, don't get hung up on the name of SuDS. So I see a lot of debates about, yeah, this is a detention basin. No, this is not detention basin. It's a pond. Oh no, it's linear and it's taking water from A to B. So I'm going to call it a swale. Understand the functionality, and maybe if you can categorize SuDS into 4 categories or 4 types: storage SuDS, infiltration SuDS, conveyance, and source control. So storage SuDS is like a pond. We use it to store the water. Conveyance is we use SuDS to take the water from A to B, and it can have a storage element. So of course, maybe we can have one SuDS that has 4 elements. Maybe this swale can infiltrate, and it's an enlarged swale to store water, and it can take water from A to B. And yeah, it can have all the elements, but understanding the functionality of SuDS will help you gain more confidence. We have the source control SuDS, it's like this green roof here, and we have the infiltration SuDS like this, the bottom left figure here. Okay, so with that, I'm going to show you an example and talk about the typical steps, or basically the steps to design and model a typical SuDS project on a master plan level. And this, I will try to cover most aspects and issues encountered when designing, modeling, and making decisions related to sizing and constructing SuDS features. And then we will see how info drainage will accelerate the process and will save time that we normally waste on design iterations resulted from the lack of spatial awareness within a hydraulic model. Now, in a typical SuDS project, the client issues a brief to the designer, communicating their objectives and saying, okay, this is what I want. And basically, I would like you to propose SuDS in this site. And this is a flood risk driven project, or maybe aesthetic driven project, or water quality, whatever. Now, you're going to get the client objectives. And then the designer needs to start with a feasibility assessment, checking basically the levels of the site. So maybe commissioning a TOFO survey, checking the utilities within the site. So commissioning maybe GPR to understand where the utilities are, how deep they are, and this is very important. CCTV of the existing drainage system, because we're going to connect SuDS somewhere. So if we cannot infiltrate, we need to find the existing public sewer. So maybe we need a CCTV so we don't connect to a pipe that has cracks, or maybe we can find this solution or do something. Maybe UXO to understand if there is a risk of UXO in the unexcluded ordinance. And then once we establish the space available for SuDS and the depth that we can go to based on all these site constraints, now we can start sketching and checking the utility, where the utilities are, and proposing possible locations. So once we
just to say, Samer, we can't see the software program. We can see the PowerPoint saying demo of info drainage. I'm not sure if you're going to plan to share the info drainage screen.
I'll just change this to.
Perfect. That's it. Yeah.
Okay. Perfect. Thanks. Thanks, Pete.
You're welcome.
Okay. So yeah, basically, once you come up with a concept design, you're going to sketch a few options And once you get all parties happy, for example, 3 officers, transport people, highway people, flood risk officers, everyone is happy with the concept design, now this is the time when we need to model the solution. So if I open info drainage, the first option that I have here is to import the a CAD layer as a background layer. And this will bring all the constraints that I talked about and the sketches that the designer has agreed on with the client. So if I import the data here and I go, give me the SuDS background. Now we see that this is the site. It's a carriageway. We're going to drain it into SuDS. And there is some runoff expected from permeable areas. So runoff from greenfield areas, and that will be captured maybe in a cutoff drain here. So we're going to have a swale that is serving both permeable runoff from the east and impermeable runoff from the carriageway. And we checked that the only possible way to discharge is a combined sewer. So we can rely on infiltration, but to help us reduce the discharge, but we need to connect to a combined sewer in the area. So we talked to the water company. The water company said, oh, this is a combined sewer. We have an objective to reduce the discharge as much as possible. And yeah, we agree with them. And this is why we need to find a solution to slow down the response, reduce the rate of the discharge into the combined sewer, and ensure that we don't flood our site. So how are we going to achieve this? If we rely on gully pipe solution, we're going to end up flushing the combined sewer during the peak of the storm. Water will shoot off really quickly in maybe 8-10 minutes. Water will be in the combined system. It will surcharge really quickly. We're going to flood upstream, and we're going to cause a problem, and no one will be happy with that. So what we need to do is try to find a way to slow down the water and capture the water in stages. And when we commissioned a topo survey, which I will import now, I will right click on surfaces and load surface, and I will import the surface here. And maybe I can. So we commissioned a topo survey, and we realized that this is a very steep site. If I can, yeah, it's a very steep site. So we see from 197 all the way to 188 here. So we need to think about these solutions that I talked about, the check dam and maybe compartmentalization, etc. So how info drainage will help us accelerate this? So in the past, we typically we would start modeling the pipe network. So if I start, for example, taking the building the junctions, so maybe I can say, okay, I have a junction here, I have a junction here, a junction here, 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 and then I can start building the connection, the pipes, and I say, okay, I have a pipe here, another pipe here, and I have a pipe here, and similarly, and then we start building the SuDS structures. Now, typically, we used to deal with, or we used to drop the SuDS structure on a triangle. And it used to be some sort of a triangle in the middle, and we get all these incoming pipes towards the triangle, and you're gonna get some pipes with the wrong length. We're gonna get some dummy pipes to get things working, and there is no spatial awareness of where the SuDS footprint is, and basically whether the size is working or not, whether the volume has been achieved. And in this case, as we can see, if I turn off the surface, this pond here is surrounded by utility, by a gas main and by a high voltage cable, and we've been given this area, maybe the top area, as a constraint. So once you're given this, we're going to see now how you can model exactly the same area in info drainage, and you can get the inlets represented exactly as they're going to be built, so you don't have to explain always to the maybe person who's CADing the drainage design, saying, oh, this is a dummy pipe, don't worry about this, you need to put this here. And normally this is when mistakes happen. I experienced it myself when a client called and say, hey, can I get you guys to upsize the pond, or maybe change whatever the location, so we moved the pond to the right, etc. Because of this disconnection between the modeling and the CAD, we ended up clashing with utilities. So and it does happen. It happens all the time. Then we have to do another design iteration and look at another solution, what we should be doing in this case, and then maybe downsizing and taking the new volumes and the new footprint, base area and top area to CAD, and checking with things, and then putting this back, because we used to see a triangle and only a little triangle in the previous software in micro drainage. Okay, and in here you can easily see where things are, where the inlets are, and where the outlets are. And not only this, not only for visualization purposes, the software will help you, or basically what the software will calculate on your behalf the time of concentration based on where the inlets are or where the outlets are. So if I want to, let's say, design this pond, you have the option of either you can import the top area as a GIS polygon and work from it. Maybe you can digitize it if you want. So you can easily go build, add stone control, and you're gonna add a pond, and you say, okay, I have a pond here. And you say, I have a pond here, and this is the top area of the pond. And then once you have it, you can double click and say, this is the, of course, we need to import the surface again. Okay, and yeah, so you can click on the pond, you see that the exceedance level has been picked from the surface, and you can say the depth is 1.2 meter, and it will calculate the base level, and then you say at 1.2 meter, the depth was 575, and you can go to the sizing calculator and side slopes. You say, if I want to go 1 in 3 or 1 in 4, or let's go 1 in 5 to make it people friendly, then, and I want to maintain the top area. So what this should be, so it can work back from the top area to the base area, or to the bottom area, or you can work from the bottom area. If you have the bottom area and you want to know what is the land take, you can call the client and ask them to purchase land. Now you can give them this number, for example, 575. But in this case, they gave us, and during the concept design, they gave us what is the maximum area that we can take, or the land take, and we worked backward. And then you can say okay to that. So that's, let's say we agreed on 178 and 575, and then you can say okay to that. And now you see this is the base area. Now when we want to connect the pipes in here, we're not connecting into the center of the pond. We're basically connecting, if I add a junction here, another junction here, we're basically connecting into wherever the inlets and wherever the outlets are. So in this case here, if I go to the connection, I can say I have this pipe section is going to go into this inlet, and this here pipe is going to go to this inlet, and that will be taken into account when calculating the time of concentration within the pond. And then once you build the downstream systems, and now we're going to do it, and we're going to take an outlet from the pond, the software will realize immediately that, okay, this is water leaving the pond, and we will see how we're going to model the flow controls and all this. Okay, and now we have the swale. So of course, once we get to the pond, you can model all sort of, you can add infiltration from the side, from the base. You can add manning, because now the movement of water within the pond is being simulated. And maybe you can redefine the center line. You see there is a center line here. Maybe you want to say, if I go to edit and I say redefine center line, and the center line is from this point to the outlet. So you can do that, because this is where water is entering the pond and this is where it's exiting. And now we're gonna model the swale. So within the swale here, if I have one section for the swale, it's gonna be steep swale, and we won't get the volumes to be utilized. So we will use a feature within info drainage called the train feature. And if I click on add train and I go to swale, I can easily say, this is the first section of the swale. And now this is the second section of the swale. And the software will understand that there is some sort of an outlet, there's some sort of control going on between these two sections. And if I want to represent the check dam will not be only one orifice. It will be an orifice and a weir. So I need to add another control and say that this is going to be a weir. Let's use a weir, and this is going to be an orifice. So the orifice, let's say it's 100 millimeter. Normally, if you have an orifice in the open, should be more than 100. But let's say 100 millimeter, because it blocks quite easily. And the width of the wheel, let's say 5 meter, depends on the check dam. And then you can say okay to that. So you see, water will get to this point, and the orifice will dictate the movement of water between the swale and the second section of the swale. Now, once we exceed the top level of the swale, the weir will be triggered, and it will be taking the water via the weir equation and the orifice equation at the same time. So now we can someone can look at it and say, okay, I see what's going on. If I double click on the swale, I see the inlet. Here, the inlets we haven't modeled yet, but I see that we have two outlets. It's quite easy, and you can determine immediately what's going on. And if I want to model how water will leave the pond and enter the swale, I can easily say, okay, this is the outlet point. This is where I have my head wall, and this is the swale inlet. So once you do that, the software will realize immediately that you have some sort of a control going on here. So you can double click on it, say this is an orifice, and the diameter maybe is 50 millimeter. And now water will be transferred towards the swale. And then from the swale, we have a tank downstream. And then from the tank, we're going to discharge into the water company manhole. So similar to what we've done previously, we're going to build the tank. And we can say, this is the tank. And this is the connection. And it's going to be from here to here. So if you notice, we don't need to add a dummy pipe, or all the pipes are being represented physically as they are. So if you export this model to a BIM model, everything is there. You won't get someone calling you and say, oh, what is this for and what is that for? And sometimes they issue construction drawings with elements that you just had to add make something work. Sometimes we add the dummy pipe so we can have a control on the second or on the second downstream pipe, etc. And it confuses people, and it's not good for BIM purposes. But in this case here, we have an outlet, swale outlet. So we take the water from the outlet. We just need to say that it's 100 millimeter orifice. And again, clients don't like 100 millimeter orifice if it's in the open, but yeah. Finally, we're gonna add a junction here and connect the tank. So we're gonna connect the tank into the junction. And of course, you would need to model the tank if it's like a 1.2 meter tank. Here, the software picked the exceedance level. And if we say let's call it 1.9. So at least we have 750, maybe 95. So we have a 1.2 meter tank and 750 millimeter of cover, because the tank structure would need some sort of a cover. So then we say, so this represents the chamber, the access chamber to the tank. And then once you say okay to that, now this is your tank. Now water is getting into the swale from a carrier drain that the council built, and it's not a water company pipe, it's a carrier drain to pick all the gullies and then have one connection into the swale. Now, in the past, we used to have to create a junction in the swale, and that junction used to have the data associated with it, and then we would connect into the junction, and that will confuse, when we export it, it will confuse the CAD people. So now you can go carrier drain, manhole, manhole, and manhole. And then you can have a pipe. And you can say this to this, and this to this, and this. Exactly, this is where the inlet is. All what we have to do is have an inlet like this. And if there is a control, you can just describe it. If it's a direct discharge into the swale, you can just put it here. And similarly, we're going to do the same here. So we're going to add the junctions, and we will model the carrier drain. Oh, I think. Okay, so now let me enhance the view and just let's take off the labels. I'll keep these labels, and we take the junction labels and the connection labels. Okay, so we have the connection exactly where they are. You don't need any dummy pipes, etc. You're aware of the spatial, you have the spatial awareness of your SuDS features. If there is a pipe here, or there is a something here that we cannot exceed, you can easily understand what's going to go on if you upscale the swale, or if you increase the top width or the bottom width. So if I double click on the swale here, I can see the exceedance level, it's been picked. And let's say if it's a 1 meter swale, the top width has been picked from the digitization. If you say it's 1 in 4, the software will calculate the base width. And if you say that the freeboard should be 300 millimeter, that will be taken into account. And you can check the levels and say, okay, the longitudinal slope is 1 in 150, for example. And manning, assuming it's a vegetated swale, should be anything between 0.03 up to 0.09, depends on the type of vegetation. So let's go for 0.03. And you can say, okay, and that's the swale model. So you see there's some sort of a representation of the base area, and in here, dash line, and then the top area here. So you have exactly, if we do the same thing here, so we say this is 1 in 4, and the depth is 1 meter, and 300 millimeter, and 150, and 0.03. Okay, so these are the all the elements of the model modeled. Now I prepared a model that is ready to be simulated, and it's all singing and dancing. So all these subcatchments have been modeled, and let me explain a little bit about the subcatchment. We have the carriageway subcatchment contributing directly to the carrier drain, and once we draw them, info drainage will detect immediately the upstream manhole. So if I delete this one maybe, and I say that I want to build a storm, an inflow and a catchment area, and I start digitizing. Now, immediately info drainage will be sensitive to the manholes within the polygon, and it will connect the catchment area automatically. Now, this wasn't possible in previous software packages, but now if you want to change the direction of or the connection of the subcatchment, in the past we used to have to delete the subcatchment and digitize it again and say, okay, now we're going to connect here. But now you can easily say connect inflow, and I want this subcatchment to go here. So you can easily do this iteration, and it will save a lot of time. I mean, if this feature was here in 2014 and 2015, I mean, it would have saved me hours and hours, maybe weeks of work, because I spend a lot of time in my life deleting subcatchments and redirecting them and doing all this associated work. So now we have these impermeables subcatchments contributing to the runs, to the carrier drain, etc. But we've been told that sometimes when it rains on the green field here, we get some permeable runoff. So to protect the carriageway, we put some swales. I mean, that was one of the reasons why we wanted swales. But at the same time, we want to account for these. In the past, we used to have maybe a node in the swale or another node and another dummy pipe, and we used to connect the subcatchment to the pipe and then connect it to the swale, or maybe have a junction in the middle of the swale. Now you can easily, if I can delete this, and if I delete that, now you can easily say, I want to have a catchment area, and you can digitize it. And it will be sensitive to the SuDS feature, and it will connect directly. Of course, that's not an impermeable area, so we need to play with the parameters and say maybe CV, or the volumetric runoff coefficient, maybe it's 0.2 or 0.3. I mean, do your studies and see what it should be. The time of concentration, this is a really, really important and a nice feature here, that you can use some equations to calculate the time of concentration, because the permeable response is not like the impermeable response. It doesn't get to the swale in 5 minutes. It will take more time with vegetation, with infiltration, with evaporation, with all these processes happening. And if you say catchment roughness is 0.4, you can calculate and you can get the travel time. So the software calculated the flow path length, and you can calculate the travel time. You say okay to that. This is for sizing purposes, and now for dynamic sizing, for when you run simulation, you can say it's okay 0.3 and 0.3, and the time of concentration, I'm going to use Friend's equation, and I'm gonna say it's 0.4 and say okay to that. And now that's 100%, and you say okay. You see the software now decided that this water that lands here, it will contribute to your swale over 164 minutes. It's not going to be in 5 minutes, which is a fair assumption. And we used to play with parameters in micro drainage and just trying to replicate this, and it's all now there ready for you. So you have more confidence, and you have something to lean to when someone asks you, who told you that it's going to be 3 hours before you get a response? And you say, okay, I used Friend's equation. It's within the software. You can see, and of course you have other equations that you can rely on, and you can read about them and see which one you want to use based on what you know about your subcatchment. So I found it really cool, and I wanted to share this with you. So let's say yes to that. And now before yeah, before I run a simulation, I wanted to show you another feature that it can even further accelerate things. So if you have the polygons, if you digitize your subcatchments and your SuDS features, let me delete all of these. Let me see what you can see on the screen. Okay, perfect. So if I delete these, clear all. If I delete all these, maybe clear all. Okay, so let's say that someone digitized the subcatchment in GIS or in another software, in CAD. You can easily now go to inflows and say import from CSV, import from GIS. And you can select and you say, give me the subcatchments. And you can say next, and you see them all here. And you can say, I want them to be green. And say okay to that, and then say next. And you can click import. Ta-da! Oh, you have all the subcatchments imported and ready to be simulated. Now, similarly, we can import the, if you don't have this pond, let's delete it. You can import the top area. I think we've done that. And you can say this is a pond. You can get the software to realize the polygon that you're bringing in a let's say as a swale or as a pond or as a dry swale, whatever. So you can say next and you can say import, and you have now the pond, which you can start, of course, playing with the parameters to sort things out. Now, these are very, very helpful when creating a network and will help you accelerate the design. Now, one last thing before we run a simulation now is when you click on the pond, you can easily go to scale, and you can scale it by, for example, 50%, and oh, sorry, this is not the final model. But anyway, what I wanted to say that when you scale the pond after you build your pond and put all the parameters, you can see whether you hit the gas main or not, and this is what we want. If I switch back to the final model, and the cool thing here is now you have validate. So if you click on validate, it will show you what went wrong with the model, and you say, okay, you have these, for example, these problems here and there. If I double click on this and I make Manning 0, and I hit analyze and I hit validate, it will show me that there is something wrong and Manning shouldn't be 0. So I need to put it back at 0.03 and say okay to that, say okay, and now I can validate, and it's okay. Now, once my site is okay, it means I can run it. Now, Pete, I'm not doing good with the time, right?
You've kind of run out of time. Bless you, but it's so nice to see, Samar, and the fact that you're bringing in all the practical issues that you've experienced in real life, and sort of showing people how much easier and quicker it is, not just to design things, but to edit them, import multiple sources and all that. It's answering a lot of the questions that are being raised. So don't worry about it, but we will have to kind of end the webinar fairly swiftly. But what I'm going to do is say thank you to everybody in terms of all the questions, because we're going to run further webinars, and there's a lot of questions that have come up on, for example, thank you, Renuka. There's things like when we're putting in an under drain beneath the swale base, how do the flow paths work between the swale at the surface and the under drain? Is it fully interlinked, or do they work independently? This is the whole thing with info drainage, Renuka, that we've brought everything together so you can now design, model, and communicate your SuDS strategies a lot quicker and easier. And what we'll do is we'll answer all those questions in kind of future webinars, if that's okay, because we are kind of rapidly running out of time. But I'll let you wrap up, Samar, and then we'll sort of hand back to Ben, and then take it from there. Is that okay?
Sounds great. Thanks, Pete. So once you run a simulation, now you get a report on all your SuDS features and what is the inflow, what is the outflow, what is the depth, what is the water level, the resident volume, and whether there is a flooded volume or not, hopefully not, and all of this, and you can see what is being generated from your SuDS for in every storm or every in the critical storm, for example. And you can also generate reports about your pipes, your manholes, your flow controls, your outlets, your inlets, everything. Even you can get a report about the subcatchments. So if I go to results, and you can see the inflows, and for example, critical storm, each subcatchment, what is the flow that was generated from it? What is the rate and what is the volume? That is extremely, extremely useful, and I will end it here. Thank you very much for listening. Apologies that I went over time. I mean, I wanted to leave 10 minutes to discuss questions, but so yeah, sorry, I didn't notice this until very late.
No problem, Sarah. But thank you so much. We're like 1:59, so there are quite a few questions, but as I mentioned, we are going to run a series. So I'd love to have Samar come back as well, and what we can do is we can build upon the questions that have come in, Samar, and then go through and answer everything in a kind of a sequence, if you know what I mean. The other bit of feedback I wanted to share with people really was the fact that apart from the kind of criteria that we gave people to vote on, were there any other things that people were finding out there? So we will share that as well, but it seems to be dependent upon the approving authorities, a lack of clarity or a lack of implementation of Schedule 3. So we are talking to folks in Wales where they have implemented Schedule 3. So we're going to run another webinar just on that to share that experience and compare that with how we're finding it in maybe other parts of the UK and other parts of the world as well. So thank you one and all. It's been really, really fascinating. A lot of interaction, a number of questions, but most of all, I'd like to thank you all for attending and thanks Samar for a great presentation. Before I hand over to Ben to show us what's coming up, Ben, talking about that. Thank you all.
Brilliant. Thanks, Pete. Many thanks to Samar and Pete for the webinar today. As Peter said, for any questions we did not have time to cover, we'll get back to you with an answer. We also have an exciting program of webinars scheduled for the coming weeks. Please look in the chat box for links to register and join us for any that are of interest. And also share these links with your colleagues. It would be great to see you there and joining us. I'll also be sharing a recording of this webinar in the coming days. Please also remember to complete the short survey that follows this webinar. In return, you'll receive an attendance certificate to use as proof of professional development. These certificates will be sent out from GoToWebinar in 5 days' time. As always, don't forget to check out our upcoming training courses. Visit our website for more details about them. And finally, a big thank you for joining us today. Have a great day, everyone.